So another important part of circuit elements are independent sources. And so on the left here, on the top left corner, we have the ideal voltage source. And these are a couple different ways of depicting ideal voltage sources. So for batteries specifically, we use this double line with essentially one of the lines being larger, and that line that's larger is the positive, and then the line that the feedback or the negative line is generally slightly shorter. And that's generally what we use as standard notation for battery ideal source. Now, if you want to go to any DC source, so a good example of just a normal DC source would be like a cell phone charger. If you took a cell phone charger and you cut the two wires that come out of it, that's a great example of a DC source, 5 volts DC. And that we use a capital VS to kind of indicate that this is a DC voltage source only. So if you have any or the common, any other voltage source that you're going to use for that, you're going to use a lowercase VS and use that symbol there. Underneath this we have the ideal current source. So for any DC current source, we're going to have the blue circle with an arrow going in the direction of the current, and the capital IS to kind of write out that this is a DC current source any. And then any kind of current source that we're going to use is the lowercase is, same symbol though. Now, I briefly mentioned before about how in ammeters and voltmeters that there's a little bit more going on there than we had previously mentioned. And one of the things that we look at is there really is no ideal voltage source or ideal current source. These are mathematical approximations that get us very, very close to where we need to be. However, you need to know that in the real world, they don't exist. So a realistic voltage source is a VS, so any source that you're going to use in this one, has a resistance to it. It's an internal resistance. And this, a great simple experiment that you can do, and you've probably already done with this, is if you take like a 9-volt battery and you connect it to the top with a wire directly and you short the battery out, essentially that battery itself starts getting really, really hot. And the wire gets hot too, but both are getting hot. The wire is getting hot because there's a current and a voltage going through that wire, and there's very low resistance, so a lot of current is trying to be dumped through that, so you get a lot of heat coming out of that. But also the battery is getting hot because the battery has an internal resistance, and that's essentially saying that as that current flows through that circuit, that flows through that loop, that the battery itself is actually getting warmer and actually taking some of that energy out as well. There's a couple really cool mechanisms for that we can look at in the future, but just know for now that any ideal voltage source has a resistance essentially inside of it, in series with it, mathematically. And then for a realistic current source, it's kind of the same deal, except it has a resistance in parallel with it. So between these two realistic voltage source and the realistic current source, things are slightly different mathematically than if you use ideal. So early on, we're going to use an ideal sources for a lot of our problems with resistors and capacitors until we start to get the fundamentals down and understand that. And then we're going to mix it up a little bit with a realistic current source. So another thing that we have, though, is dependent sources. So if we talk about independent sources, that means they always stay the same. So a 5-volt source is always going to supply 5 volts to our circuit. A 3-amp current source is always going to supply 3 amps to the circuit. However, dependent sources are not like that. Dependent sources can change. So there's a couple different types of dependent sources. The first one on the top left is a voltage-controlled voltage source, so a VCVS. And essentially this is saying that the voltage changes as a function of voltage. So as voltage goes up, maybe the voltage on this one goes up faster, or some way of doing that. There's a couple different ways that we're going to look at these in upcoming slides, so we're going to do a little bit of a brief glance over now and more complex in a bit. A current-controlled voltage source, which is the one underneath of that, essentially is saying the voltage is going to change as the current changes. So if current goes up, maybe the voltage goes down. Or if current goes down, the voltage goes up. In the top right-hand side, we have a voltage-controlled current source. So that's going to be a VCCS. And that's saying essentially the current is going to increase as the voltage decreases. Or in the very bottom, we have a current-controlled current source, a CCCS, where essentially we're saying as the current increases in some other part, then the current in that part decreases. So we're going to go through these in more depth in a bit. Just know that essentially for a dependent source, it depends on something else in the circuit. It could be something external to the circuit. It could be something nearby in the circuit. Essentially, though, the voltage and the currents for a dependent source change, and they don't have to change linearly either. You can have nonlinear changes, you can have curves, you can have a whole bunch of different functions represent inputs into dependent sources. So remember previously we looked at the ideal voltage source, which is what we're generally using early on for the math calculations. An ideal voltage source is essentially a direct, perfectly vertical plot of voltage versus time. And same with an ideal current source. This is perfectly horizontal. There is no slope to that. However, dependent sources can change. So dependent sources here, we have a VCVS, a voltage-controlled voltage source. So that's saying that as the Vx increases, the Vs is also increasing. You're going to get a slope to that. So again, slope is going to be the rise to the fall, and we're going to be able to calculate out Vs from that. So the slope in here is essentially going to be your alpha, and that's going to be how we calculate the rise to the fall. So again, this VCVS is a linear slope. You can also get curvilinear slopes. You can get much more advanced slopes going on. The important part to know is for these dependent sources that you don't have a linear, you don't have a perfect ideal current source, a perfect ideal voltage source, and that means you're going to have pieces in the circuit that are going to depend on the values of other pieces in the circuit. So a great example of an equivalent circuit using dependent sources is actually an op-amp circuit. And we're going to study these significantly more in later chapters, and they're really cool. Op-amps, you can do a lot of awesome stuff, a lot of interesting math, and a lot of sensor analysis and that kind of stuff. However, for now, we're just going to look at the op-amp circuit, and I want you to keep this in the back of your mind to when we get later in the course. But the op-amp itself can be approximated as an equivalent circuit with a dependent source. It has a couple internal resistances, and here you're going to have a voltage that depends on another voltage coming in. So you're going to get that V2 equals AVI. And so the op-amp, the whole point of an op-amp is to take essentially some kind of signal in and manipulate it, usually boost it or increase its amplitude, increase the amount of voltage that it's going to output. And that gives you from a very quiet signal coming in to something very loud. So an op-amp essentially can be thought, again, it's an amplifier. So you can think of that as your MP3 player outputs a very tiny little signal. And you want that to essentially set the music for an entire dance room. And the op-amp is going to take that little signal and make it into a much larger signal that can power larger speakers. So with that being said, this is a great example of an equivalent circuit with a dependent source. We're going to go into this much more detail when we get to op-amps, but I just wanted to kind of show you that now. So here is a basic example of a circuit with a dependent source. And what we've got here is we have a 10-volt normal DC source, looks like a battery, going through, and there's two resistors, and there's a V1, which is a current-controlled voltage source. So essentially what that's saying is the voltage given out at that point, the V1, is going to equal to I1. And I1 we see over in the middle as the current going through that 2 ohm resistor. So how do we solve this? These are actually relatively easy to solve. And so my method for doing this is I make a break around the VI. So that that CCVS I remove. And I don't connect the wires there, I just pull it out imaginarily. And that's going to leave a break, which means no electricity is going to flow through that area because there's a break in the circuit it can't go through. So essentially that's going to mean that 5 ohm too, because it's just sticking off. There's no place for the current to flow through that. That doesn't exist as either. So all you're going to get then is that battery, that 10-volt battery, and that 2 ohm resistor. And we remember that V equals IR, And so we can solve for V equals IR. What we're going to do then is we're going to solve what I is equal to. So we're going to take I1, which is the current at that portion going through that resistor, and I is going to equal to the 10 volts divided by 2 ohms, and that's going to be 5 amps. And then as simple as it is, now we plug that 5 amps that we got back into the other equation to solve for V1. So V1, it says, equals 4I1, and I1 equals 5, so that's going to be V1 equals 20 volts. Now, we're not solving this case for anything else. That's the end of this problem. But later on, then, we plug that CCVS back in, and that's how we can solve for the entire circuit, for some other parts of the circuit as well.